The next talk is provided by the Professor Hiroshi Murakami. And okay, so the screen is on. So the title is Single Precision Calculation of the Iterative Refinement of the Eigenpairs of a Real Symmetric Defined Generalized Eigenproblem by using a filter composed of the single resolvent. So quite a long title. Okay.
Thank you.
Please keep, okay, go ahead.
Do you hear me?
Yes.
So by using the filter, we solve eigenpairs of a real symmetric-definite general eigenproblem whose eigenvalues are in a specified interval. The system of linear equations to give the action of a resolvent used in the filter is solved by some direct method. To reduce both costs to factor the matrix and to store the factors, the filter we use is a polynomial of a single resolvent. Such a filter, however, does not have a good shape in the transfer function, and the residuals of the approximate eigenpairs will not be small. We iterated the combination of orthonormalization and filtering a few times to improve the approximate eigenpairs. Filters composed of a single resolvent, I explain. Eigenpairs of a real symmetric definite general eigenproblem is approximated whose eigenvalues are in the specified interval from A to B by using a filter. A filter is composed of a resolvent. Here, shift rho I are complex numbers. An application of the resolvent reduces to solve a linear equation for Y, whose coefficient C rho is A minus rho B. In this study, some direct method used to solve it. The shifted matrix C rho is real symmetric when rho is real, and is also positive definite when rho is less than the minimum eigenvalue. When rho is imaginary, C rho is complex symmetric and non-singular. The system of symmetric linear equations is solved by the modified Cholesky decomposition and forward-backward substitutions. When a system of linear equations of a large size is solved by some direct method, there are following computational bottlenecks: the amount of computation for matrix decompositions, the amount of storage to hold factors of matrices. To reduce these amounts, especially the amount of storage, in this study, we minimize the number of resolvents that compose a filter to only one. Two types of filters composed of only a single resolvent are these. For type 1, the shift rho is real, and the eigenvalue interval from A to B must be at the lower end. For type 2, the shift rho prime is an imaginary, and the interval may be located anywhere. Here, GS is the upper bound of the filter transfer function magnitude in the stop band, and gamma and gamma prime are real constants, and I is the additive operator. Filters composed of only a single resolvent cannot have good shapes in their transfer functions. Transfer functions cannot make steep changes in value. Mu, the ratio of the width of the transition bands to the width of the passband, cannot be made very small. When GS is set to a very small value, the max-min ratio of the transfer function in the passband from A to B will be large. If this max-min ratio is very large, after the filtering, the rates of required eigenvectors contained in the set of vectors tend to have different orders of magnitudes. By the filtering in the set of vectors, those eigenvectors whose transfer rates are larger are enhanced, but those ones whose rates are smaller are diminished. In the filtered vectors, the information of eigenvectors with smaller transfer rates tend to become less accurate. Some of the approximate eigenpairs may not meet the required accuracy or may be missing. Therefore, it may be necessary to improve the approximate eigenpairs obtained from a single filter application. Iterative refinement of eigenpairs by using a filter. So far, we have assumed the filter is applied only once. Even the filter's transfer function is not good in shape, the approximate eigenpairs can be improved if the combination of orthonormalization and filtering is iterated a small number of IT times by the following procedure. Step 1, Let Y be an initial set of M random vectors. Step 2, iterate the following IT times. That is, Y is B orthonormalized to obtain X, then X is filtered to obtain Y. Step 3, considering the shape of the transfer function, constructs the required approximate eigenpairs from both X and Y. In the iteration, M, the number of vectors, is updated to the effective rank, which is determined by the 𝐵-orthonormalization. Orthonormalization for each iteration prevents the tendency of those vectors, eigenvectors, with relatively small transfer rates to reduce information by the filtering. The principle of the method is well known as the orthogonal iteration. We show the experiments. The system environment is the machine is Oak Forest Packs 1 node, CPU's Intel Xeon Phi, that's night running, peak performance 3 teraflops in double precision, memory 16 gigabytes of MCD RAM and 96 gigabytes of DDR4 memory, and number of threads we used is 204, that is 3 times of the number of cores. The test problem, a 3D Laplace eigenvalue problem with zero Dirichlet boundary for a cubic region with a side length of pi. This is a Laplace equation. For FEM discretization, a real symmetry definite generalized eigenproblem is obtained. This is a generalized eigenproblem. Sides of the cube are equidivided into n1 plus 1, n2 plus 1, n3 plus 1 subintervals to make finite element. This figure shows the concept of finite element partitioning. Finite element basis, that is a trilinear function we used. Matrix size of A and B is expressed by this expression. Lower bandwidths of A and B are this expression. For this test problem, the exact eigenvalues can be calculated by simple expressions. The number of eigenvalues in an arbitrary interval can be counted also. By using a filter, we approximate all eigenpairs whose eigenvalues are in the interval from A to B. This definition, relatively residual of approximate eigenpair. The quality of an approximate eigenpair, lambda V, can be evaluated by the relative residual defined as this equation. The approximate eigenpair is accurate if theta is small. Theta is independent from the normalization vector V. Theta is invariant if A and B are multiplied by a constant. When phi is the angle between two vectors AV and lambda BV in the Euclidean space, then the following holds. This is a geometrical interpretation of the relative residual. Experiments of iterative refinements in single precision. Finite element partitioning of a cube, we used 50 by 60 by 70. A and B have then size, matrix size 210,000 and lower bandwidth is 3051. Single precision has 7.2 digit precision in decimal, is used for numbers and arithmetics. Single precision has little margin for accuracy. However, recently, power savings through low precision calculation has been attracting attention. For some systems, single precision is much faster to calculate than double precision. Designs of filters for present experiments. For lower-end eigenpairs, the filter is a degree n Chebyshev polynomial resolvent with a real shift. For interior eigenpairs, the filter is a degree n Chebyshev polynomial of an imaginary part of a resolvent with an imaginary shift. We specify the filter's transfer function by a set of 3 parameters, mu, gs, and n. We prepared 4 filters with different settings to solve lower-end eigenpairs or interior eigenpairs. Both mu equal 1.5 and gs is 10 to minus fifths for the all cases. Degree n is set to 4, 6, 8, and 10. The values of gp and gs over gp are shown in the table. Next table. Settings and properties of the filters. N is 4, 6, 8, 10. For lower eigenpairs, the established GP value is like this, and GS over GP is these numbers. For interior eigenpairs, GP is larger than the case of the lower end eigenpairs, that is better, and also GS over GP is also smaller. GSGP is the rate of reduction per iteration by the filtering. The larger the value of GP, the better the filter property. The smaller the value of GS over GP, the better the filter. These are figures of the filter's transfer function magnitude. The left side is for the lower end eigenvalues, filter for the lower end eigenvalues. The right side is filter for interior eigenvalues, but showing only the right hand by the symmetry. The n is 10 degrees 10, 8, 6, 4 is red line, green line, dotted blue line, and dotted brown line. And this also 10, 8, 6, 4th degree, red, green, dotted blue, and dotted brown. The shift of resolvent of each filter. The shift of the resolvent is shown for each filter with parameters to solve eigenpairs whose eigenvalues are either in the lower end interval 0 to 100 or in the interior interval 100 to 200. For the lower end eigenpairs, the real shift law is these numbers for each degree. For interior eigenpairs, for each degree, imaginary shift law prime is these numbers. The real parts are common, but imaginary parts are gradually increased. We show the graphs. This is for the lower end interval case, real shifts. This red is degree 4, green, blue, brown means 6, 8, 10. For the interior interval 120, 200, this black line, and the imaginary shift law prime is this red, green, blue, and brown. That is degree 4, 6, 8, 10. So example 1, lower end eigenpairs calculated. In the lower end interval 0 to 100, there are 402 eigenpairs to be solved. The union of the passband and the transition band 0 to 150 contains 764 eigenvalues. The number of initial vectors we used is 800. That is more than 764 of the above and would be sufficient. Result is shown. These are tables for each degree filters, 4 degree, 6 degree, 8 degree, 10 degrees, number of approximate eigenpairs and maximum relative residuals. The true number of eigenpair must be 402, but at the first iteration of the filter, the number of eigenpairs are wrong. But after the second iterations, number of eigenpairs are all correct. The numbers inside the parentheses are by the calculation in double precision. Outside is a single precision. The max relative residuals gradually reduces as iteration proceeds, but saturated. Double precision goes still going reduced. We show the graph for the lower end eigenpairs. The left side graph is for the single precision calculation. The right side graph is for double precision calculation. Red, green, blue, and brown shows different filters for degree 4, degree 6, 8, and 10. And the double precision calculation, the number of iteration increases, the maximum relative residuals goes down like straight. But single precision calculation, it saturates at certain points, 3 iterations. This may be 4 iterations. These graphs are relative residuals calculated in single precision for every eigenpairs we required. Red dots are first iteration, green dots are for the second iteration, and blue dots are third iterations, and brown or orange dots are for the fourth iteration, etc. This is degree 4, this is degree 6, this is degree 8, and this is degree 10. And if we calculate in double precision calculation, this is a first iteration, second iteration, third iteration, etc. For degree 4 filter, degree 6 filter, degree 8 filter, and degree 10 filter. This shows the error of eigenvalues calculated in single precision calculation. Green lines are for the second iteration. Filter is applied twice. Blue lines are filter is applied for 3 times. And orange line are for 4 times. For the degree 4 filter, this is for degree 6 filter. This is degree 8 filter. This is for degree 10 filter. So this graphs are for double precision calculation. The absolute error of eigenvalues. Degree 4 filter, degree 6 filter, degree 8 filter, and degree 10 filter, and iteration, second iteration, third iteration, fourth iteration, etc. Gradually, the error of eigenvalue also reduces. Elapsed time in seconds are shown for the low-end eigenpairs using 800 initial vectors, degree 4 filter, 6 filter, 8 degree 8 filter, degree 10 filter. The data is in parentheses by the double precision calculations. We show the graphs. The left side is single precision calculation. The right side is double precision calculations. As the number of iterations increases, of course, the elapsed times increases, but this number is 750 for double precision case, 1,500. So we can easily understand the timing, elapsed time is half for the single precision calculation compared from the double precision calculation. For the interior eigenpairs case, example 2, we calculate the eigenpairs whose eigenvalues are between the 100 and 200, between 100 and 200. There are 801 eigenpairs to be solved. The union of the passband and the transition bands contains 1,192 eigenvalues. The number of additional vectors used was 1,300. That is more than 1,192 of the above number and will be sufficient. The results of the experiments are shown. These are tables of number of approximate eigenpairs and also maximum relative residuals. The correct number of pair must be 801 for the degree 4 filter, 6 filter, 8 filter, degree 10 filter. The number of eigenpairs are wrong at the first iteration, all are wrong. But after the second iteration, all numbers of eigenpairs are correct. And the maximum relative residuals reduces as the iteration increases. Double precision's case also reduces. This is a graph of the graphs. For single precision calculation is the left side, double precision calculation is the right side. As the number of iterations increases, the logarithm of the maximum relative residuals reduces like this, like this, like this. Double precision calculation also straight reduction in a lines. This is relative residuals in single precision calculation for degree 4, degree 6, degree 8 filter, degree 10 filter for each eigenpairs. At the first iteration, even the number of eigenpairs are wrong, so very large relative residuals. But the second iteration and the third iteration and the fourth iteration, this overlapped, gradually improved. For the degree 6 filter is like this, like this, like this. In a double precision calculation, relative residuals are like this: degree 4 filter, 6 filter, 8 filter, 10 filter. The first iteration, second iteration, third iteration, and fourth iteration. First, second, third, fourth, so on. The absolute error of eigenvalues in single precision calculations are like this. The horizontal axis are eigenvalues, the vertical axis are logarithm of error of eigenvalue. The green lines the second iteration, the blue lines third iteration, and the orange lines fourth iteration, etc. And also, this also, this also, this also. These are same level of the errors. In the double precision calculation, the second iteration and third iteration, fourth iteration gradually reduces. This is degree 4, degree 6, degree 8, and degree 10. Elapsed time in second for the interior eigenpairs using 1,300 initial vectors, the degree 4 filter, degree 6 filter, 8 filter, 10 filter, numbers inside the parentheses are double precision calculations. We show the graph. The left side is for the single precision calculation, right side is double precision calculations. As the number of iteration increases, the elapsed time in second goes up, but from comparing the left graphs and right graphs, this is 1,500, this is 3,000. So the elapsed time is almost half for the single precision calculation compared from the double precision calculation. Conclusion, we show the conclusion. We made experiments to solve generalized eigenvalue problem by using a filter. The generalized eigenvalue problem tested was derived from a finite element discretization of the Laplace eigenvalue problem on the cube. To minimize resource requirements, especially storage, we used filters composed of only a single resolvent. However, such filters have poor transfer properties. The present iterative approach to improve eigenpairs worked well to overcome the poor properties of the filters, even when the calculation was performed in single precision. On a system of Intel Xeon Phi 7250, nice rounding, we observed that both storage requirement and elapsed time of single precision calculation were about half of those of double precision calculation. This is a conclusion. I have an appendix, but I think it's a good time to stop here.
Okay, thank you very much. So is there any question or a comment? So here's one question on the chat by Benson Muit. Is it expensive to convert from single to double to be able to do mixed precision?
Yeah, we recently make mixed precision calculation research. Yeah, but surely the converting the format from single precision to double precision or double precision to single precision is not cheap, I think. You are correct.
Okay, he says thanks. Any other question? So I have one question, and I'm sorry, but I'm not familiar to the mathematical issues here, but then I'm interested into the performance. So you said you use one node of the Oak Forest Parks with it actually has the 68 physical cores, and you ran the over 200 threads for one node. So how do you parallelize your code?
Using OpenMP.
Using OpenMP, and is there any data sharing between the thread, or just run each thread separately?
The current implementation of the solving linear equations are level 2 plus technology. So it's not level 3. It's not so good performance. I guess if we change the algorithm in block manner, we could have a better performance, like 10 times faster, maybe.
Okay, you mean that there is no effect of the cache hit?
Yeah, but some part of the cache effect, I think cache is effective. I think effective.
Oh, maybe before that, did you use cache mode or the other MCD-RAM?
Yes, cache mode.
Okay.
Where is that? Yeah. Yes, cache mode.
I see. But if you, as like you say that it's only level 2, maybe the cache mode of the MCD-RAM doesn't work so well.
Not so well, but some parts.
Okay, I see.
I think it's astonishing using single precision calculation to using only single precision, we can calculate the eigenpairs so well.
Okay, is there any question? Okay, if so, thank you very much.